Have you ever stopped to think about the everyday magic that's happening right there in your kitchen? You know, that perfect piece of toast? It doesn't just happen. Today, we're going to pull back the curtain on the simple yet brilliant physics that makes it all work, the purely resistive AC circuit. And we're going to do it by looking at your humble toaster.
And really, it all boils down to this one question. How does a plain old wire get hot enough to do that? Well, the answer reveals this perfect synchronized dance that's happening inside those wires. So let's break it down and see exactly how that wire turns electricity from your wall into that glowing bread toasting heat.
Okay, first things first. Before we can even talk about the toaster, we need to understand the kind of power we're dealing with, the electricity that's literally flowing through your walls right now. Because, it's not just any old electricity. It has a very specific personality. That's right, the power in our homes is alternating current, or AC. Now, this isn't like the steady, one-way street of electricity you get from a battery. Oh no, AC is constantly changing direction. It's surging forward, then pulling back, then surging forward again, over and over, super fast. And this constant back and forth, it is absolutely key to our whole story. So that brings us to our three main characters in this whole electrical story. To understand what's going on, you just need to get to know these three players. I like to call them the push, the flow, and the obstacle. So first up, we've got voltage. This is our push. The best way to think about it is like a pump in a water pipe, but a really frantic one. It's not just pushing water one way, it's constantly pushing it forward and then yanking it right back. This electrical pressure builds up to a peak, drops to zero, reverses, and does it all over again in this smooth, beautiful sine wave. Okay, so if voltage is the push, then current is the flow. It makes sense, right? This is the actual movement of electrons, shuffling back and forth inside the wire. And naturally, this flow is going to perfectly mimic the push it's getting from the voltage, creating its very own matching sine wave. And our third character is resistance, the obstacle. See, every material fights back against the flow of electricity, at least a little bit. Sticking with our water pipe analogy, you can picture resistance as a really narrow, tight squeeze in the pipe. That pump, our voltage, has to work a lot harder to shove the water through it, and all that extra effort creates friction and, as we're about to see, a whole lot of heat. All right, so we've met our three players. Now for the really cool part, the heart of this whole thing, how they all interact. Because in the simple world of a toaster, their timing is everything. This right here. This is the secret sauce. In a circuit that only has resistance, like that heating wire in your toaster, the voltage and the current are perfectly in phase. What does that mean? It means they are in absolute, perfect lockstep. They peak at the same instant. They cross zero at the same instant. They reverse direction at the same instant. This perfect timing means there's no wasted effort. Every single bit of push is instantly turned into flow, which is why it's so incredibly good at making heat. Just look at how this breaks down. It's kind of beautiful, right? The moment the voltage, our push, hits its maximum power, the current, our flow, hits its top speed. The very instant the voltage decides to switch directions, the current switches right there with it. There is zero delay. They're like perfect dance partners, moving in complete and total harmony. So, what's governing this perfect dance? Well, that brings us to our next part. You see, this perfectly timed performance isn't some weird, complex new thing. It's actually controlled by one of the oldest and most fundamental laws in all of electronics. Yep, good old Ohm's law. You've probably seen it before. Voltage equals current times resistance. And the real beauty of a simple resistive AC circuit is that this simple, elegant law applies at every single moment. Think about that. Even though the voltage and currents are constantly changing, flying up and down their sine waves, if you could just hit pause and freeze frame them at any single instant, Ohm's law would still be true for that 1 microsecond. The voltage at that moment will always equal the current at that exact same moment multiplied by the resistance. It's a constant relationship. So let's make this real. Let's say the heating wire in your toaster has a resistance of 12 ohms. Right at the moment the AC voltage coming from your wall hits its peak of 120 volts, the current flowing through that wire will peak at exactly 10 amps. The math is that clean, that direct, precisely because they're so perfectly in phase. And here's the payoff. This is where it all comes together. We've talked about the push, the flow, the obstacle, and the timing.
So for our final section, let's connect all the dots and see exactly how this electrical theory makes your breakfast.
So here's what's happening. That perfectly in-phase current gets shoved through that high-resistance wire. The electrons making up that current are just constantly bumping into and colliding with the atoms inside the wire. And every single one of those trillions of tiny collisions releases a little burst of energy. When you add all that up, that energy shows up as intense heat. And because that current and voltage are in perfect sync, the conversion from electricity to heat is incredibly direct and efficient. It's just pure, raw power making that wire glow red hot. And hey, this isn't some special trick just for toasters. This exact principle, using resistance to turn electricity directly into heat or light, it's the basis for so many common things. Those old school incandescent light bulbs, electric stoves, those little space heaters. At their core, they're all just big, carefully designed resistors doing their thing. So there you have it. Resistance takes electrical flow and turns it directly into heat, all because the voltage and current are working together in perfect sync. But that brings up a really interesting question, doesn't it? What happens when a part of the circuit doesn't just resist the flow, but actually tries to store it for a little while? What does that do to our perfect little dance? Well, we'll get into that next time.